the stream. Okay, chapter 4. That sounds horrible. Chapter 4. Begins on page 111 in your book. Derivatives, yeah. It's a good thing to end on. Okay. We're going to start with trying to motivate this. Describe a line with negative slope. What does a line with negative slope look like? Going downhill, right? From left to right. Yeah. How about positive slope? Uphill from left to right. How about zero slope? Horizontal line?
Like this table.
Yeah. Well, one hopes that tables are horizontal. What does the magnitude of the slope of a line tell you about the line? So it's how fast the rate of increase or decrease. And what does the sign of the slope of a line tell you about the line? Increasing or decreasing?
All the way back down.
Oh, yeah. Yeah, slope of lines. Okay, give an intuitive representation of a line tangent to a curve at a point. What is the difference between a tangent line and a secant line? So if you have some curve, I don't know, and you're looking at, that is going to be our point C, F of C. What is the tangent line, intuitively speaking?
Tangent lines only intersect at one point.
Yeah, they only intersect at one point. Well, almost. Tell me about this one. What's the tangent line right here? Horizontal line. If I continue that line, how many times does it intersect my curve? Twice. So that definition doesn't quite work. That's the one I was looking for. But it doesn't quite work. Yeah, it's parallel to the slope of that point. So you have to add parallel. Now, what's the difference between a tangent line and a secant line? Secant intersects a curve at 2 points. And so you just move that one point to the other and you keep your little intersections until the second point becomes the first point. And that gives you the limit definition. So the secant line intersects at 2 points. It intersects a neighborhood of x. Intersects a line in a neighborhood of x at 2 points. I'm just going to do intersects at 2 points. That's not a technical, but it's close. So let's look at this function x and x minus 5 squared. What is the tangent line at the curve at x equals to 5? What is the derivative? Well, let's actually go through the process, but yes. So it's product rule, so it's 1 times x minus 5 squared plus x times 2 times x minus 5. So what is that derivative when x is equal to 5?
3x.
Yeah, just plug in 5 for all the x's. You get 0 and 0. So what is the tangent line at the curve x equals to 5? It has to go through 5, 0, right? And it has slope of 0, so it's actually equal to y equals 0. Yeah. It goes right through. Well, I missed. Like that. We remember that from Calculus 1. We've done that ever since we can remember almost. Ever since we were babies. Okay. Consider the function f of x equal x squared. Use the method of secant lines to find f prime of 0. So what we do with the secant line is we choose any points away. One of them has to be our point 0, 0 because it says f prime of 0. That means x equals to 0. So that's 0, 0. And then we can choose any other x point here, and that would be x comma x squared, right? So we're going to plug it in, find the slope of the line joining. I'll put slope in front. Slope of line joining the 2 points. So yeah, slope is rise over 1, so it's going to be x squared minus 0 divided by x minus 0. Well, that's going to be x squared divided by x, and I'm assuming x is not equal to 0 here. So I can cancel that, and that just gives me x. So as x goes to 0, what happens to m? It has to go to 0 too. So as we let x approach 0, m approaches 0, and so that says the slope at 0 is going to be 0. That's our secant method. Now, we so desperately want to get limits in there, so that's where we're headed.
No, we don't have limits.
We don't have to have limits? I should make this full screen, then I think we can see all of the limits. Yeah. Go away, little green thing.
That formula.
There we go. Yeah. Let f take d to r, with x naught accumulation point of d and x naught is in d. For each x and d different from x naught, you define t of x to be f of x minus f of x naught over x minus x naught. This is our slope, rise over run. The function f is said to be differentiable at x naught if and only if t of x has a limit, and you write f prime of x is equal to the limit as x goes to x naught t of x. That's the same thing as the limit as x goes to x naught. F of x minus f of x naught over x minus x naught, which is what you guys used in Calculus 1. Now we have an alternate definition. What is the difference between definition 2 and definition 3?
It's like the delta x from back in the day.
Yeah, so this would be like f of x plus delta x minus f of x over delta x. Are they the same? Why would they be the same? Are they the same definitions? Yeah, because this is our delta x right here. And then that right there would be the f of x right here becomes the x plus delta x, x naught plus delta x. So x is equal to x naught plus delta x. So they're essentially the same definition. Mhm. I went backwards.
That's the wrong direction.
Yeah, I did. Okay. Prove that the definition of the derivative and the alternate definition of the derivative are equivalent. That means that they're the same. So we thought about why they were the same. To show that they are the same, I have to start with one and get to the other, and then I start with the other and get to the first one. So, assume definition 2. That's the original definition. Yeah. Let x naught be an accumulation point of D and x naught in D. Then the limit as x goes to x naught of f of x minus f of x naught over x minus x naught exists. That's what we're assuming. Well, we want to make that into an x naught plus t. But to be able to show that x naught plus t, that definition works, I can show it works for any sequence of t sub n's. Okay? So, yeah. Let t sub n be any sequence converging to 0.
Never seem to hear those sequences.
Nope, they always appear. Converging to 0 such that x naught plus t sub n is in D for all n. That's possible because x naught is an accumulation point. So I have to have this sequence of terms converging to it. Now, what do I know? I know this limit, I'm going to call this 1, by substitution into 1, and since the limit exists, I know that the limit as n goes to infinity of f of x naught plus t sub n minus f of x naught over x naught plus t sub n minus x naught has to exist. Because this limit up here exists, it exists for any sequence converging to x naught.
And the x naughts on the bottom.
Yeah, the x naughts on the bottom cancel, and what do we get?
They still have on top over the t sub n.
Oh, that's not going to fit there. I have to put it down below. Now, t sub n is an arbitrary sequence. And all of this I know is equal to f prime of x naught. So, yeah, I have to move this down. Yes, we proved one direction. Since all of these sequences converge to the same value, since this holds for all t sub n, we have limit as t goes to 0, f of x naught plus t. Okay, this is not all going to fit on this page. Let me go get another page. That's not what I want. What page? Append a page. There we go. Okay. Since this holds for all t sub n, we have limit as t goes to 0, f of x naught plus t minus f of x naught over t is equal to f prime of x naught. And hence definition 3 holds. Assuming definition 3 and showing definition 2 is exactly the same. So what do we do when it's exactly the same? Similarly, definition 3 implies definition 2 holds. Thus, the definitions are equivalent. Yep. Not a hard proof. But a necessary proof because we interchange those definitions all the time. So we really need to know that they're the same thing.
Can I do a question on the test?
It's never appeared on a test yet.
Oh.
Sorry. Okay.
Oh, sorry to ask.
You have to ask, yes. You have to know. Theorem 4.1, it says, suppose that f takes d to r with x naught an element of d and an accumulation point of d. Then f is differentiable at x naught if and only if every sequence of points in d minus x naught converging to f of x naught, you have this sequence converges. This is the same thing as definition 3. So we're not going to prove it. Same thing, definition 3 comes from theorem 2.1. Just know that you can use sequences to prove your limits.
Why do you have different fields? Should they be the same?
It is just another way of saying it. Okay. We're going to start a series of examples here, and we want to figure out what differentiability is telling us about the shape of our functions. So what is the behavior of our functions? So consider the function f of x equal to absolute value of x for all x in the reals. Is f differentiable at x equals to 0? Prove your claim. And is f continuous at x equals to 0? So what does absolute value of x look like if you graph it? It looks like a V. Yep. There's a sharp corner right there. Wherever you have a sharp corner, you don't have a derivative. Because the slope is different. What is the slope on this side? 1. What's the slope on this side? -1. So is it going to be differentiable at 0?
I
No.
was wondering why we never went that way. I never remember having talked about that.
Yeah, it doesn't have a derivative at 0 because they're different on either side.
Now we have to prove.
Now we have to prove it.
Another function like that?
Are there functions that don't have derivatives at points? Yeah, there are lots of functions that don't have derivatives at points. There are none as simple as this one, except a jump function, because it's discontinuous, so therefore it can't have a derivative. Yeah.
Are we going to prove it by contradiction?
No, we're actually just going to take two sequences and show that we have different limits. Remember, a derivative is a limit. For the limit to exist, it has to be the same no matter which set of points you use to get in. So I'm going to define f taking r to r to be f of x equals the absolute value of x. And consider the two sequences. I want one coming down from the positive side. What sequence should I take coming down to 0 from the positive side? 1 over n. N equals 1 to infinity. So let's look at the limit as n goes to infinity of f of 1 over n minus f of 0 over 1 over n minus 0. What is f of 1 over n?
Uh,
1 over n, right? Yeah. What's f of 0? Also, for the sequence minus 1 over n, we're going to have the limit as n goes to infinity, f of minus 1 over n minus f of 0 over 1 over n minus 0. What's f of minus 1 over n? Yeah, negative 1 over n. Mhm.
So it's 1 over n over 1 over
1 over n minus 0 over minus 1 over n. I forgot the limit. Yeah. The limits are different. Limit as n goes to infinity of f of 1 over n minus f of 0 over 1 over n minus 0 is not equal to the limit as n goes to infinity f of minus 1 over n minus f of 0 minus 1 over n minus 0. Thus, f is not differentiable at x equals 0. Is f continuous at x equals to 0?
Yeah.
Yeah. We're not going to show the continuous part, but I mean, we know how.
I already did it.
Yeah. So, what does this tell you? Continuous does not imply differentiable. Continuous does not imply differentiable. Just because you know your function is continuous does not mean you know your function is differentiable.
If it's differentiable, you know that it's.
Yeah, next class period. We'll prove that theorem. That's exactly right. Differentiable implies continuous. Or is that this one? I think it is this one. Yeah, that's theorem 4.2. A little bit later today. Now, look at this function right here. X sine 1 over x for x not equal to 0, and 0 for x equals to 0. This function looks like this. And it just oscillates more and more rapidly as it goes to 0. We want to use the normal formulas from calculus for derivatives to determine those values for x for which f is differentiable and those values for which f is not differentiable. So let's just take the derivative of this part right here for x not equal to 0. What would be the derivative? Product rule, right? So derivative of x is 1, so we get sine 1 over x plus x. What's the derivative of sine? Cosine 1 over x times the derivative of 1 over x. Mm-hmm. So this x and that are going to cancel. And we get a sine 1 over x minus 1 over x cosine 1 over x. Is this function 1 over x cosine 1 over x or sine 1 over x, are they well defined at 0? No. But for any other value of x, they work. So this is differentiable if x is not equal to 0. Now, let's look at x equal to 0. The limit as x goes to 0 of f of x minus f of 0 over x minus 0. So f of x, when x is not equal to 0, is x sine 1 over x minus 0 over x minus 0. So x sine 1 over x, the x's are going to cancel. You get limit as x goes to 0, sine 1 over x. Now, that function, if you guys recall, looks like this and gets very, very close. But it oscillates between plus or minus 1. Does it have a limit at 0? No. So that does not exist. Therefore, f is not differentiable at x equals to 0. It's differentiable every place else, but it's not differentiable at x equals to 0. Okay, they're going to change this function a little bit. Here you have an x squared. Now, what does an x squared look like? And it's going to oscillate, but it gets driven smaller much faster. We want to know, does f have a derivative of at x equals to 0? So let's check the limit. Limit is x goes to 0, f of x minus f of 0 over x minus 0. What is f of x if x is not equal to 0? So x squared sine 1 over x. What is f of 0? 0 divided by x minus 0. So this becomes x squared sine 1 over x divided by x, but that is equal to, yeah. And what is that limit at 0? Actually, x sine 1 over x has the limit of 0 because it's driven in by the straight line. So the limit is 0. That exists. So f prime of 0 is going to be 0, and f is differentiable at 0. That was a derivative was undefined at 0. But this is the limit of x sine 1 over x, which is just the previous function continuous. The previous function is continuous at 0, but it's not differentiable at 0. That makes sense?
Can you scroll up to the
See here, when we got down to the limit for the derivative, we have that right there. But yeah, yeah, we didn't have that function left over down there. That's the derivative of it. And on the next one, right here, this was the old f of x, but we have a new f of x.
Okay.
Yeah. So this is continuous. X sine 1 over x is continuous at 0, but not differentiable. This one is continuous and differentiable. But the derivative, look at f prime of x when x is not equal to 0. What is f prime of x when x is not equal to 0? Plus x squared cosine 1 over x. Minus the x. Is this derivative continuous at 0? No, because of that cosine 1 over x, it doesn't have the x in front. So this is not continuous at x equals to 0. So this one, f is continuous at 0. F prime of 0 exists. F prime is not continuous at x equals to 0. Yeah.
Wait, you just said that if it's differentiable, it should be continuous. Right?
Yeah, but the derivative doesn't have to be continuous.
Oh,
Yeah, the derivative doesn't have to be continuous. The function has to be continuous, but the derivative doesn't. Yeah, you have to. They'll catch you.
But why we have to show that the function is not continuous or continuous? Why?
Because we're going to start talking about in analysis 2, we're going to talk about families of functions that are continuously differentiable. And that has very special properties about it. What makes a function's derivative always exist? The next, the third, fourth, fifth. When can you not take any more derivatives? that's the question we're going to be asking in analysis too.
Probably not.
So we're heading there.
I believe you guys are taking
I know David is. Why, you should be.
Probably this week.
I thought Dr. Brown said it's an option.
For BS, aren't you BS mathematics?
No, yeah.
Oh, I thought you were BS. Well, we'll see. I have taught that class to only one person before. It works well because whenever you want to ask me questions, you're the only one there.
Never want to be the author.
Mhm. Sorry, you have to pay attention.
You're the
I
highest.
will notice if you don't pay
You're
attention.
the highest one.
I guess that is.
They better be paying attention, dummy.
I'll be the best and the worst at the same time.
Yeah, there you go.
But David, if you get an A, then you won't be the worst, you'll just be the best.
That's true. You can't fail on me though, I mean. That would not look good to fail your only student. That's not guaranteeing a pass, but
That'd be terrible.
that would be terrible.
One student failed.
Yeah, no, we won't go there. Okay, so the next example, you have an x cubed sine 1 over x. So let's actually look and calculate the derivative right now. For x not equal to 0, what would this be?
3x squared sine whatever x plus
Cosine what?
x.
Times minus 1 over x squared. Simplify that. Minus x cosine 1 over x. We know this is continuous because I know that that's continuous and that's continuous. So this is continuous on our question, David.
So basically, if there's just an x in front of it, you know it's continuous.
Well, we've already looked at the case of x sine x. That was the very first example we did. And we know that x sine x looks like this. And x cosine x is the same picture except a shift off, and you just can't see the shift when it's jumping that close. So they're essentially the same graph. There's just a phase shift off of it. So I know that they're both continuous because it's driving it down to one point right there.
Is this already doing on the homework?
What would be a-
No, I think your homework is a little bit different than that.
What would be a function that
It's like the fewest one, the absolute one, and it's the common.
They're similar. I mean, you're using this, one of them is different. You're talking about uniformly differentiable. Okay,
That's the next topic.
so tell me, is f prime differentiable?
Let's find out.
The limit of it.
So limit as x goes to 0 of f prime of x minus f prime of 0 divided by x minus 0. We'd still, what would this limit be then? Limit is x goes to 0 of f prime of x. Because I know it's continuous, I can plug this limit in. I know this went to 0, and I know this went to 0.
So that's kind of just like in the observation, basically.
Yeah, that's just by looking at the limits. Yeah. So you're going to have f prime of x. We have to plug in the f prime of x. That's 3x squared sine 1 over x minus x cosine 1 over x minus 0 all over x. Well, the 0 is going to go away, and I can factor out the x.
Yes.
So that becomes a 3x sine 1 over x minus a cosine 1 over x. Does that have a limit at 0?
No.
No. So f prime is not differentiable. So in this example, f is continuous everywhere. In fact, at x equals to 0 is what we're concerned about. F prime is continuous f prime of 0 does not exist.
So
Double prime?
Yeah, f double prime of 0.
if it's differentiable, then it's continuous, but if it's not differentiable, then it's not continuous.
Differentiable implies continuous, so let's answer this question this way. P implies Q. Does not P imply not Q? No,
Well-
this is fallacy of the inverse. So not differentiable does not necessarily mean not continuous.
Not
It could be.
Oh, man, I just need to be a-
Yeah. Yeah, does not imply. Not differentiable does not imply not continuous. Mhm. Okay. From the above examples, if you were trying to identify what we've learned, if a function is continuous, it doesn't have to be differentiable. If a function is differentiable, the derivative does not need to be continuous. And a function is not differentiable at those points where it is not continuous. So those are the three things that we saw. We're going to have a theorem that kind of summarizes it all. Theorem 4.2, let f take d to r be differentiable at x naught, where x naught in D is an accumulation point. Then f is continuous at x naught. What's the hypothesis?
These are differentiable.
Yeah, all that stuff.
Assume hypothesis.
Yep.
Assume everything else is there.
Except that F is continuous at X.
Dot, 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 dot.
By the way, why do they insist on putting this accumulation point of D in there in that definition? Who really needs to know it's an accumulation point?
Because we're going with limits.
Limits. If you're going to take a limit, you have to know it's an accumulation point. You have to know it's the limit of some sequence. What we have to do is show that f is continuous at x naught. Now, when we were dealing with limits, how did we show something is continuous when we were dealing with limits?
Delta.
Well, that's the delta epsilon proof, but this is the limits one. It's our theorem 3.1. If the limit as x goes to x naught of f of x equals f of x naught, then f is continuous at x naught. So that's what we're going to try and do here. What we want to do is come up with some way of looking at the limit of f of x. So we have to come up with a way of writing f of x in terms of the derivative. Since f is differentiable, then I think they call it t of x. Okay, so let's write this first. We'll break it into two sentences. Let t of x be equal to f of x minus f of x naught over x minus x naught. Then, since f is differentiable, I know that the limit as x goes to x naught, t of x is equal to f prime of x naught. Okay, and that exists. Now let's rewrite our f of x. F of x is equal to f of x minus f of x naught plus f of x naught, right?
Yeah.
Okay, so that gives me the numerator part here. Now I need to make that divided by something. So I can write that as f of x minus f of x naught divided by x minus x naught times x minus x naught plus f of x naught. Are we good so far? Okay. Let's look at each of these things. The limit as x goes to x naught, t of x is equal to f prime of x naught. The limit as x goes to x naught of x minus x naught is equal to what? 0. And the limit as x goes to x naught of f of x naught is just equal to f of x naught, right? So the limit as x goes to x naught of f of x is equal to the limit. By the way, I can write this as t of x times x minus x naught plus f of x naught, right? Wait for it. There we go. So that's the limit as x goes to x naught of t of x, limit as x goes to x naught of x minus x naught, plus the limit as x goes to x naught, f of x naught. That's by our algebra of limits. But that is equal to f prime of x naught times 0 plus f of x naught, which is f of x naught. Well, if that's equal to f of x naught, what's our conclusion?
Well,
It's continuous.
that was actually really fast. Please, when did you read it? First to work out, but- Has that one been on the show all the time?
Yeah.
That one's a lot more.
Like, you see,
Yeah.
I heard that.
I think this is theorem 3.1, but I wouldn't be sure about that number, but we know which one it is. It's equivalence theorem for limits and continuous. Okay. F is continuous
So it's 4.2.
at x naught. Well, this is theorem
Oh.
4.2 that we proved, but I think it's by theorem 3.1. Mhm. So that one is a very straightforward theorem. That theorem says continuous implies, differentiable implies continuous. So the previous, so the theorem 4.2, let's write this down. Differentiable implies continuous. The contrapositive of this would be what? Not continuous implies not differentiable. Those are the two things you know from this theorem. Differentiable implies continuous. Not continuous implies not differentiable. You don't know anything else about it. What?
No.
No.
If I was saying if it's not differentiable, then it's not.
So not differentiable implies not continuous. That's false. And continuous implies differentiable. That's also false. So this is a converse, and this is the inverse. The two things that you can't do. You know, the regular one and the contrapositive are, those two will have the same truth or falsities form. That is the end. I wanted to give you a hint on your homework. Let me see if I remember which one it was. Yeah, tell me which homework problems, have you guys looked it up?
3, 6,
41,
9, 10.
43.
3, 6, 9, and 10. It's number 6. Yes. You are looking at this limit right here. Limit as h goes to 0, f of x plus h minus f of x minus h all over 2h. That's what you're looking for. You want to show that that's going to be equal to f prime of x. What you do know is that f of x plus h minus f of x all over h, if you look at that limit, that's f prime of x, right? And you do know that the limit as h goes to 0. And now what I'm going to do is write it as, which way did I write it? F of x minus h minus f of x. That has to be over a minus h. That is also equal to f prime of x.
Wow.
Okay, so you're coming from the opposite direction. That minus sign is what you need. And then when you combine these together, what you're going to get is, if you add these together, your f prime of x, well, actually subtract them. The f prime of x is going to cancel, but the f of x is going to cancel, but this should be a minus. Yeah. So that your f primes will add together. You're going to get two f primes.
And you have two.
Yeah. And then divide by the 2, which you have right here. Because that 2, you can write that, limit as h goes to 0, f of x plus h minus f of x minus h over 2h is equal to 1/2 limit as h goes to 0, f of x plus h minus f of x minus h all over h. So you can take that 1/2 out in front. So you're splitting it up as to two derivatives, but make sure you get that minus sign to come down. That's your hint on that one. The rest of them, I think you should be able to do. Yeah, number 10, be careful, because at one point you're going to divide by a minus sign with an inequality, so make sure you flip your inequalities when you divide by your minus sign. I'm not sure on that. Did I get that right? That's bothering me. Yes, you are going to be adding them. That is very correct. And then when you have this minus over x minus h minus x, so x, and then you have a minus h in the denominator. That should be a positive.
It's the same.
Yes, yes, it is positive. Because you can interchange. Here, let me show you where this comes from. It ends up being positive. It's x minus h minus x. The x's are going to cancel and you get your minus h. But that still gives you a positive f prime of x because it comes from that value right there. And so then when you add them, because if you add these together, then this is a minus h in the denominator, and this is a plus h in the denominator. So you have to take that minus out in front when you add it together, and then it becomes subtraction.
Right.
Yeah. So you're actually adding them, but then that minus comes out and gives you subtraction. There you go. Now that feels right. Okay, we're done early today. What do you know? Unless you guys had more questions.
I have a question. 43, number 3.4. That's the one that you do in class. I'm not sure that
It's the,
I'm doing it right.
it's continuous, show that f of b is less than y, less than f of a.
So you just have 3 cases for that one. So you have f of b is less than or equal to y is less than or equal to f of a, right? So case 1, f of b is strictly less than y is less than f of a. Apply the theorem. Yeah, but you can do it shorter if you just break it up into cases. The one I did in class had strict inequalities, but you can mimic it and do it that way, and that's not a problem. But if you don't want to do it that way, then you have 3 cases. The next case would be f of b equals to y is less than, and then you're just choosing c equals to b and you're done. And then the third case, f of b less than or equal to y is equal to f of a. You choose c equals to a and you're done.
Do we have outline for 4.2? Is that happening? in
That is
class?
due before you leave on break, and it's what we're doing for class. So if you want to do it ahead of time, you can,
Okay.
but that is the actual what's happening in class.
Okay.
You're welcome. Looks like you got a package.
Yeah, my sister's up here.
Nice, and you haven't even opened it.
I know she won't let me though unless she's watching.
See it?
Yeah.
Oh, so you have to wait till you can Skype
Just
her.
open it, just act like you open it.
No. You just open it now, just have it back in.
You're gonna have to tell her everybody tempted you.
Exactly.
So that's what you're doing, Kalai. Does that make sense?
It makes sense, I do similar to that as well. Yeah.
So yeah, as long as
I
you're,
did similar to that.
yeah, you can, or you can mimic what I did in
I
class.
just combine those stuff into just one.
I need to see 3 separate cases. Don't try and do them as one because you can't apply the intermediate value theorem unless you have a strict inequality. So you need that.
Chapter 3 is my worst chapter. So,
It is for most students.
yeah, the find the interval of x one is a little bit between x two and x equals one. Well, I enjoy finding this.
G of x equals x e to the x minus 1. Apply IVT.
Is this a proof?
No, it's just find an interval. And they said the interval has to be length 1, so something like 0 and 1, or 2 to 3, or something like that. Consecutive integers would be what I would try.
Right.
And if you get them to be opposite sign, because you want to find someplace where g of something is equal to 0. So that means you have to find your a has to be either less than or greater than 0, and g of b is going to be the opposite sign. And you get to choose a and b. So it would be like try 0 and 1 and see what you get.
Right. So I have to show that or?
No, you just tell me what the interval is and tell me why. Yeah,
Or tell you.
tell me what the interval is and tell me why by plugging the endpoints of your interval in and seeing that they're opposite sign.
And then,
Mm-hmm. So what values do you think you want to try for your interval?
0 and 1 because-
Yeah. Because when you plug in 0, that one becomes 0 and minus 1, so that would be less than 1. When you plug in 1, it's going to be bigger than 1 and bigger than 0. Mm-hmm. So it's 0 to 1, a equals 0, b equals 1. Since g of a is less than 0, g of b is greater than 0. Mm-hmm.
Or, so I suppose that f from the interval AB goes to interval AB is continuous, prove that there is at least one fixed point in AB.
So then g of x equals f of x minus x.
What?
Do it just the same way as the one we were just talking about.
Okay.
G of x equals f of x minus x. You're gonna have three cases. You have the case that f of a is bigger than a, with the case, and f of b is less than b. In both of these cases, you're done. Because you want to know when is f of x equals to x. So both of these you're done. This one, you're just gonna make your g of x be f of x minus x and apply your intermediate value term. Plug in g of a and g of b and see what you can come up with.
GBH Boston.
Okay.
Is what?
Major funding for Norfolk is brought to you by the Park Foundation, dedicated to education and quality television.
Why does it work for the VHS tape and not for the DVD?
Because there's something not picked up to the TV. That is my assumption.
Well, now I know. I get to watch it on Wednesday. I mean, video tape on Wednesday.
Is there only 3 cases for this?
Mm-hmm.
So then G of A would be greater than 0,
Mm-hmm.
and G of B would be less than 0.
Mm-hmm. So that means there has to be some C so that G of C equals 0. But if G of C equals to 0, what is f of C equal to?
If G of C equals to 0, then f of C has to be equal to C.
Yes. That's exactly what you're looking for.
Okay. So for this, it doesn't ask for f of G of X equals to 0. Oh, okay.
Yeah, because you want f of x minus f of x to be equal to x.
So if I assume that f of A is equal to A,
Then you're done already.
then f of A, which we want.
Yeah. So then you have just that other case to look at.
Okay.
I'll have them by Wednesday. I left them at home. I've read a few more of them, but I'm not finished with them. But I'll have them by Wednesday.
Thank you.
You're welcome. I'm gonna turn that projector off.
Sounds like it's dying.
It does. Oh, you know what I haven't done? Stop the recorder.